There it goes. Okay, so our recording is in progress, so that's wonderful. All right, it just took a while to connect. So today we're going to be talking about discrete probability distributions and how we use them to do statistics. So basically, let me begin by sharing my browser with you. Okay, and again, I'm just going to show you where we are in the course. We're currently in week 12, and essentially we're doing discrete probability distributions today and continuous probability distributions on Thursday. Let me just remind folks, I know we don't meet on Wednesdays, but in case you do have live online classes on Wednesday, tomorrow is Veterans Day. And in honor of Veterans Day, there should be no classes being held. Okay, so you want to check with your instructors if you have Monday, Wednesday classes. Okay, so again, the notes I'm going to be using are right here, discrete probability distribution notes, if you want to print those off. I'm also going to be doing a few additional examples to illustrate how you use discrete probability distributions, how you create them. Okay, so I'm going to begin by sharing my tablet with you. And again, this takes me a minute. So I appreciate your patience. All right, and let me share that screen with you. Okay, so now everybody should be able to see my notes that say section 3.4, discrete probability distributions. I'm going to leave the chat open, okay, so you can comment. But again, feel free to unmute yourself if you've got a question and you don't want to type it in the chat or it takes too long. Now, these notes have lots of words, okay? So I'm going to just kind of summarize what we're looking at. Again, the idea here is to kind of distill some of the information that's in the reading and the videos, but please understand, you're kind of still expected to look at the readings and the videos. I'm getting the impression that some folks just try to jump into the homework without doing any of the reading, and that's just going to confuse you. Okay, so again, I'd recommend use these notes, use the reading, use the video to get enough background information that the homework makes sense to you. Okay, so the first concept I want to introduce is this idea of a random variable. Okay, now you're used to algebra where you've got just variables, right? A random variable is kind of a little bit different. You can think of it as a variable that relates the outcomes of a probability experiment to their probabilities. Okay, it's kind of like what we used when we talked about expected value in the last chapter. Okay, so capital letters are usually used to represent the random variables, and lowercase letters represent outcomes. Okay, so if you see a capital X, you can think of that as a random variable that relates all the outcomes of an experiment to their respective probabilities. A lowercase x is pretty much like the specific outcome you're interested in, say like 5 heads out of 10 flips of a coin. Okay, here's kind of the notation that they'll use like in problems, or you might see in your reading. The probability that a random variable equals a particular outcome. Okay, so this would be saying, for example, a random variable is equal to a 5 means you managed to get 5 successes out of 10 flips. That's what it means, okay? So our book, I think, uses this notation, but some other books might say the probability of X, okay? The reason I'm showing you the notation is because it can be confusing, all right? And it's important to understand what the notation means so the reading and so whatever else you're doing makes sense. Right, so here's an example, right? You're flipping a coin. The results are either heads or tails, okay? So basically you could use a random variable to represent the outcome, and you could assign a numeric value like 1 to heads and 0 to tails. So you would say the random variable x equals 1 would indicate that you got a head. The random variable equaling 0 would be that you got a tail. And then you could assign probabilities to those, right? For a fair coin, each of those would have a probability of 0.5. Okay, so that's kind of the idea. Now, that's a pretty simple, probability distribution, but it's part of what you would consider a more general category of probability distributions. So let's talk about the vocabulary words discrete and continuous, which you've kind of seen before, certainly in calculus. I know the idea of continuous has come up. But discrete things in mathematics, okay, refer to data that is countable, okay? So likewise, discrete probability distributions, okay, connect to discrete random variables, okay? And what are those? Those are random variables, capital X, that take on specific countable values, okay? Discrete data values. And what that means is they're countable. Oops. Now, what do I mean by countable? Well, you can think of countable things as mapping to your natural numbers, 1, 2, 3, 4, 5, and so forth, okay? As opposed to continuous data, which is measurable, okay? Continuous data maps not to the natural numbers, but to real numbers. For example, in between any two real numbers, you can put a third real number, okay? So, for example, measurements usually map to real numbers, right? If I'm measuring a temperature, it can be 45.5 degrees or 45.6 degrees. And then if my measuring instrument is precise enough, you can imagine a measurement in between those two, right? 45.55 degrees, okay? So that's the idea of continuous data. Whereas discrete data is strictly countable, okay? So again, you can represent a discrete probability distribution with data points on a graph, okay? And you can also put them in a table, and you can assign a probability to each value of that discrete probability distribution. Now, again, here are, they say a discrete probability distribution has to satisfy the following outcomes, but pretty much any probability distribution has to satisfy the following outcomes, okay? And that basically is all your probabilities, any specific outcomes probability, has to be between 0 and 1. We said that when we started talking about probability in the last unit, namely, if you are doing work with probabilities and you get an example that's -5 for a probability or 14.3, you've done something wrong because probabilities are on a continuum between 0 and 1, with 0 meaning the event is impossible and 1 meaning the event is absolutely certain to occur, okay? So that's just a condition of probabilities, all right? The second condition down here is all of the possible outcome probabilities have to add up to 1. What that means is you didn't leave out any. First of all, they don't overlap. The outcomes are mutually exclusive. They don't overlap. All right, that's how come you can't get bigger than 1, okay? And they cover all possible outcomes. All right, so the first condition means you're not counting anything more than once. They don't overlap. And the second condition means you didn't leave anything out, okay? You managed to get all of the possible outcomes that the event can have, okay? So that means all of your possible outcomes sum to 1, okay? This lets us use the complement rule for probability, right? For example, if I want to know what's the probability that I got at least one outcome being what I want, I can always say, well, that's 1 minus the probability that none of them came out the way I want. Okay? In order for that to be the case, all of your probabilities have to sum up to 1. That lets you use the complement. Okay, so these are 2 conditions of probability distributions, and it's a way you can verify if somebody gives you a table and they say, is this a probability distribution? You're going to look for 2 things. You're going to look for, in the probability column, you're going to make sure every value is between 0 and 1. And then another check you have to do is add up all the probabilities and see that they sum to 1 within limits for rounding errors. Okay? So if you get 1.000002, you're good. That's essentially 1. Okay? That's within the limit of rounding. Okay? So let me stop and ask here. Anybody have questions about the criteria for a probability distribution? These 2 conditions. Are we good? Okay, I'm not seeing any questions in the chat. Okay, so let's take a look at some examples. Okay, so I realize a lot of these examples are frankly kind of lame. Okay, bags with marbles and balls and cards and dice. And I understand that. We're trying to make sure everybody understands the probability concept. So we use stuff that's real easy to figure out. Okay, like marbles in a bag. And then hopefully we'll graduate onto more relevant probability experiments for business applications. Okay, so again, the reason we have all of this stuff that's kind of lame is just to make sure everybody understands the concept. Because again, they're really clear to see what you're dealing with. Okay, so let's say we have balls in a bag. Okay, we've got 15 of them. And they're labeled with the numbers 1, 2, 3, 4, 5. The probability of selecting a ball with number X on it is given by this rule. Okay, X over 15. So for X is 1, 2, 3, 4, and 5. So what this means is the higher the number on the ball, the more of them there are in the bag. Okay, so they say, let's show that this meets the criteria to be a discrete probability distribution. So what I'm going to do is I'm going to make a table. Whoops. And I'm going to try to show that the outcome over here and the probability of the outcome meet these criteria. So I have 5 outcomes that are possible. Okay, and then I'm going to use the rule to determine the probability of the outcome. Remember, I take the outcome and I divide by 15. So the probability of drawing a ball with a 1 on it is 1 out of 15 because only one of the balls in the bag has a 1 on it. Okay. Probability of getting a 2 is 2 out of 15. Okay, 3 out of 15, 4 out of 15, 5 out of 15. So most of the balls in the bag have a 5 on. Okay, so the first thing I have to check are all the probabilities between 0 and 1. Okay, and if you look at my column over here, okay, all you're checking is that all the numerators are less than the denominators, okay, and nothing's negative, okay? So again, I can know that 1/15 through 5/15 are fractions that are between 0 and 1, so that's great. Then what I have to do is add up the probabilities. And check, do they sum to 1? Okay, so I'm going to do that. Everything has a denominator of 15. So I'm just going to take the numerators and add them. 1 plus 2 is 3, plus another 3 is 6, plus 4 is 10, plus 5 is 15. Okay? So basically, I can say, yes, it meets the two criteria. Here's criterion 1. Here's criterion 2. And I checked. Okay? So you can use a table to represent a discrete probability distribution, as long as your table meets these two criteria. Now, please also realize it's very easy, okay, once you have this table, to compute the expected value of drawing a ball out of the bag, right? All I have to do is take each outcome and multiply it by its probability, okay? And then add those up. That gives me the expected value. So once I have this probability distribution, I'm in good shape to do expected value. All right? So again, another way to represent such a probability distribution is a histogram. Okay? So again, remember, usually with a histogram, your vertical axis is frequency. Here it's going to be probability. Okay, so over here I've got probability P of X. And down here I have my X values. Okay, my highest P of X here is 5. Okay, so I can do that. Or I can say, well, I can make this a 1 up here. Okay, and then I can put 15 little marks in here. But again, that was a bad idea. It was very hard to count by 15s. So let me do it this way. Okay. Okay, so basically this is my probability, and these are all over 15. Okay, and then you can put your values down here of your random variable. And again, the histogram's pretty easy to draw. You just count your outcomes, okay? So up here at the table, this was a 1. Okay, my 2 was a 2, and so forth. And 3, and 4, and lastly, I've got 5. Okay, so here's my histogram, okay? And again, given the what I've got going on here, you can see the number, as the value of X goes up, it's more and more likely I'm going to draw a ball up with that number on it, a marble or whatever they are, balls, okay? So the area of each rectangles is the probability that that outcome will occur. So again, 1 by 1/15, 2 by 2/15, and so forth. Okay, they're all 1 wide. Okay, so once you add up the heights of all the bars, you're going to get a probability of 1. Okay, so again, 1 wide by 1/15, 1 wide by 2/15, right? The area of the distribution has to sum up to 1. Okay, so again, it's important to realize with all of these probability distributions, area is equal to total probability. Which again equals 1. Okay, and that's going to be a general consideration as we look at all of these. Okay. Another thing I've mentioned a couple of times is this idea of expected value. And again, I'm not going to read this to you. But again, what you want to think of it as is a long-run average value. Okay? And again, for probability distributions, long-run averages is your mean. Okay? Now, there are formulas for means of discrete probability distributions. Okay? So you can use the idea of probability distributions to develop these formulas. Okay? But again, rather than doing that, I'm just going to show you a couple of formulas, okay? So let me just put these here, okay? So for discrete probability distributions, okay, it's a little bit different than a sample. Here are the general formulas, okay, for probability distributions. You've got a variance here, okay, that's represented by sigma squared. And remember, this is for a discrete probability distribution, not a sample, okay? So again, you're going to add up the probability of each event, okay, times the square of its deviation from the mean. That gives you the variance, okay? And then remember, standard deviation is just the square root of the variance, okay? So if you've got to figure out the standard deviation of a probability distribution, here's the formula to use. Again, called probability times the deviation of that outcome from the mean squared, okay? So let's take a look at a particular discrete probability distribution, okay? There are lots of different ones, okay? We're really only going to look at two of them in detail in this course, okay? Because this is more properly part of a full-blown statistics course. But the two we're going to look at are the binomial, and one you already know, but you don't know what it's called. It's the hypergeometric. You know it as NCR, okay? So we're going to look at those two, but there's lots, okay? And the most common one, probably far and away, is the binomial one, okay? And again, just to review binomial criteria, all right, it's important when you're working with probability distributions, the most important thing is to make sure the distribution you've selected is actually valid to use for the situation you're in. So the binomial criteria are, we're doing the same experiment n times. Okay, the trials are independent. Okay, so that means the outcome of one trial doesn't affect the probability going into the next trial, okay? Which essentially means you're sampling without replacement, you're sampling with replacement, you're not taking things out of the pool, or your pool is so large, if you take a few out, it won't matter, okay? You won't affect the probability on the next trial, okay? And there are exactly two outcomes, success and failure. Okay, and remember, lots of times with binomial experiments, you can recast a situation in such a way that you can turn it into a binomial experiment. So for example, if I'm rolling two dice, you might say, I want to know the probabilities of all the outcomes of all the sums. Well, there's lots of different outcomes. That's technically not binomial, but you can say, I want to know the probability of rolling a 7. If I call roll a 7 a success, I've turned it into a binomial experiment, okay? Because then I can calculate probability of 7 as a sum, probability of not 7, okay? So again, here are the binomial criteria from before. And again, here is the idea of a binomial random variable, okay? Again, capital X, where it's equal to the number of successes of the experiment. Okay, so again, here's the binomial formula that you can use, but you can also use binom PDF, okay, or binom CDF on the TI, or you can actually use the binomial calculator I embedded in our course. Okay, so on the TI, this is in your distributions menu. Okay, and let me just show you over here. where it is in our course. Okay, here's our course. Remember what I did? I kind of created a separate module down here for you with all the tools, online tools and calculators. It's under the final exam and textbook stuff. And I kind of organized it by topic. Okay, so over here we've got binomial probability calculator, hypergeometric probability calculator. I put it in the probability section because that's the first place we saw it. Okay, so again, please make sure you're comfortable with this, especially if you're one of the folks without a TI-84. Okay, I'm not asking you to use this rule to calculate binomial probabilities. Okay, use the tool. Okay, or online calculator. All right. So again, remember, we have, this is the combinations of n things taken x at a time, the probability of a success raised to the number of successes, and the probability of a failure, 1 minus p, raised to the number of failures, which is just the number of trials minus the number of successes that we care about. Okay? So that's what we've got. All right? And we've got the number of successes. If I'm talking about a probability distribution, x can go all the way from 0, no successes, all the way up to n, the total number of trials. So if you think of this in terms of a coin flip experiment, right, and I'm interested in the number of heads that I get out of 10 flips of a coin, well, I could get 0 heads, which is highly unlikely, but possible. And I could also get 10 heads, which again is highly unlikely, but possible. Okay? So that's the idea behind a probability distribution. Okay? So if we want to figure out mean and standard deviation of the binomial distribution, there's established formulas for these. And if you go on to take more advanced statistics classes, they'll show you the formulas for all of the probability distributions, mean and standard deviation, because it's just kind of a shortcut. We don't want to have to figure it out every time. So for a binomial distribution, the mean is, right here, the number of trials times the probability of success. If you think about it, it makes sense. Okay? If on average, 20% of the things coming off your production line are defective, how many defects would you expect in a sample of 100? Well, 20% of it, 0.2 times 100, about 20 defects, okay? So this is kind of an intuitively simple thing to understand. The standard deviation, not so much, okay? So there's a formula for it. And again, it's the square root of your number of trials times your probability of success times your probability of failure. Okay? So again, these are kind of neat formulas to have, again, for binomials. But let's see to actually, what it's like to actually use them. Okay, so there's a 43% chance that a person 65 years or older will enter a nursing home at some point in his or her lifetime. I have a group of 100 people who are 65 or older. Find the expected number of people who will eventually enter a nursing home along with the standard deviation. Now, again, you might think from looking at expected, you're meant to calculate expected value. And you could, but you need the whole binomial distribution with the probabilities up to 100, right? 0 successes to 100 to do it. That's tedious. I don't want to do that. So expected is average or mean value. Okay, so that's what you need to do when you look at the words here. You need to realize expected number is average or mean. Okay, for a binomial, that's according to our formula, n times p. Well, let's see if we can find those. There's a 43% chance, that's our p-value, okay, that a person 65 or older will enter a nursing home at some point. And then here's our sample size. Okay. So we have the information from the words in the problem. Okay. And all I'm going to do is multiply those two together. So of my group of 100 people, I'd expect about 43 of them to enter a nursing home at some point in their life. They asked me also for standard deviation, which is the square root of NPQ, where Q is 1 minus P, right? It's the probability of a failure. So let me figure that out. That's 1 minus 0.43. Okay, so again, my Q is 0.57. Right, then I can put that in here. 100 times 0.43 times 0.57. Again, to do this on a calculator, just take the square root, okay, and then put everything in here. I'm going to show it to you on my Web 2.0 calculator. Again, assuming a lot of you don't have the TI. Okay, so first thing I want to do is square root, and then I want to put my values in here. So first I have my N value, then I have my P value, and then I have my Q value. Close the parentheses. Okay, double check up here. It looks like what you wrote on your paper. All right, so again, I have 0.495 as my standard deviation. And again, remember, you can click on this to put the formula back in the calculator if you need to adjust it or try it for different N and P values. Okay. So I'm going to go back here and I'm going to say this is approximately 4.1. Okay, and again, remember the idea behind standard deviation. What it says is, on average, you'd expect 68% of your area under your curve, your probabilities, to be within one standard deviation either side of the mean. So let's say this is about 5. Okay, I'd expect 43 plus or minus 5 people to give me 68% of likely nursing home residents, right? Likely to enter nursing home. Okay, so 43 minus 5, anywhere between 38 and 48 people. Okay, that range in my sample should roughly account for 68% of the data, 68% of the people. Okay, so that kind of gives you a ballpark of the probability. Okay, anybody questions at this point? Let me just stop and ask questions. Can you just give me a shout out, yes or no? How are we doing? Questions?
Sorry, what do you mean again by 68% likely?
Okay, we're going to talk about this in detail in the next section. It's part of it's something called the empirical rule. Okay, and it has to do with anything that can be modeled by a normal distribution, which turns out lots of probabilities can, as long as your sample is large enough. Okay, so think of it as a rule of thumb, because I know telling people 4.95 doesn't mean anything to them. So yeah, it's a standard deviation, but unless I have another one to compare it to, so what? Okay, so I'm trying to show you what it means in context of this problem. If we round it up to 5, what I'm saying is between 38 and 48 people, I would say that I have a 68% chance of being right if I say between 38 and 48 people will enter a nursing home. And this comes from an empirical rule we'll talk about in the next section. but it gives you a better understanding of what the standard deviation is telling you. Okay, I'm saying, again, 68% of my probability is between 38 and 48% of the people. Okay, so if I had a sample of 100 adults over 65, and I wound up with only 20 of them winding up in a nursing home at some point in their life, that would be very, very unlikely. Okay, as would having 90 of them winding up in a nursing home. Those are unlikely results. Now, we're not going to be doing any kind of inferential statistics in this class, but a lot of you are headed to GBS 221 where you are going to do hypothesis testing. So I'm trying to show you kind of what the variance, what the standard deviation is telling you about the probabilities. Okay, so again, don't worry too much about the 68%. You're not going to need to use that here. You're just going to need to be able to calculate the standard deviation. I'm trying to give you an idea of what use that number is to you. Does that help?
Yeah.
Okay, good. Don't hesitate to ask, because again, in introductory statistics, I find one of the things that drives me nuts as a teacher is there's not a lot of explanation as to what good is this? Why am I learning this? I'm just pushing formulas around. Okay, so I'm trying to give you some idea of what it would be used for. Okay, so please don't ever hesitate to ask, this doesn't make sense. I'm there with you, believe me. Okay, so let's take a look at some other discrete probability distributions. And like I said, these are not ones you're going to necessarily use in this course. The only one of these you've actually used already is this hypergeometric one. Okay, but we've called it NCR. Okay, we haven't called it by its actual name. The Poisson distribution, that's the first one, and the geometric distribution we'll talk about and what they're used for. I'll also show you the formulas for them, but don't worry, they're on your calculator should you ever need them, okay? So the Poisson distribution, okay, is kind of used for calculating the random number of things that happen in a certain time period, okay? So let me put this over here first. You've got these on your calculator, Poisson PDF, okay, and Poisson CDF. This is on a TI-84. There are also calculators that do Poisson distributions online. I haven't included any of them in our course because I'm not going to ask you to use them. I'm putting them here in case you need them in the future. Okay, so what is all this stuff? Okay, so a Poisson random variable follows this formula. Okay, the probability of the random variable equaling a certain outcome I, where I is any one of these outcomes. Okay, and this other funny thing is a Greek letter lambda, and lambda is the mean of the distribution. Okay, the mean of the distribution. And that's something that's usually given to you or something you'd be able to calculate. But what would you use it for? Okay, things that are usually modeled with a Poisson distribution are number of misprints on a page in a book. Okay, number of wrong telephone numbers that are dialed in a day, number of customers waiting in line for anything, okay, in a certain time period. And again, the number of vacancies occurring during a year in a federal judicial system, okay? So how many times does this happen? Okay, you can see this is a little different from a binomial, okay? Now, in case you're wondering and you haven't figured it out yet, PDF gives you the probability of the random variable being a particular X value. CDF gives you the probability that it is less than or equal to a particular value, okay? It's cumulative. And this is true of all the distributions on a TI, okay? If you use the probability density function, PDF, you get the value is equal to one specific number. If you use the cumulative density function, you get the probability less than, from 0 on up to your X value. The beauty of the online calculators is they make this extremely clear. You put in all the parameters needed to find probability, and it will list for everything the exact value, less than, equal to, greater than, on the outside of. I mean, it's really nice, okay? The TI-84 is a little tricky because it's only going to give you from 0 to X here. You've got to figure out anything else, okay? So again, let's look at another distribution that you are not going to need to use in this course, okay? But what's interesting about the geometric distribution, it's used to describe the outcomes of a binomial experiment with two possible outcomes, okay? Where you want to know how many trials will it take to get your first success. You can think of that. That's pretty useful, right? Okay? If I'm a gambler, I might want to know how many times do I have to roll this die till I roll a 6, all right? Or 2 dice and roll a 7, okay? Suppose you want to know in a population that 10% of your accounts have accounting errors in them, okay? Accounts are inspected until you find the first error, okay? How many accounts do you have to look at to find the first error, okay? How many products do you have to look at to find the first defect? Okay, those are all geometric probability distribution questions where P is the probability of a success. Okay, and again, this is also on a TI-84. It's called GeoMet PDF and GeoMet CDF. And again, there are certainly online calculators for it. Again, if you ever want to find a probability distribution online calculator, just search for the name of the distribution, like geometric, probability, and then calculator. Okay? Poisson probability calculator. You'll get a bunch of hits. Okay? And most of them are pretty self-explanatory to use. Okay? So please don't feel, oh my gosh, I need a TI-84 or I can't do any of this. It's not true. And in some regards, the online tools are better, okay, because they're more modern, okay? They give you a lot more options with the output, okay? So anybody have any questions on what these are used for? Okay, so basically I'm asking questions on how they're used. We're not going to actually calculate any of them, okay? But hopefully I've given you enough information in these notes that if you had to use an online calculator or Poisson PDF or GeoMet PDF on your TI-84, you'd be able to, okay, to get a calculated probability, okay? Again, I'm trying to give you enough to take you forward with statistics. Okay. The next discrete probability distribution, again, we've used, okay? We've actually used this, okay? And we haven't called it hypergeometric, but you'll recognize the formula for it, okay? The hypergeometric distribution is used to describe experiments where you're drawing or sampling n times without replacement from a pool that contains two different types of objects, right? Like men or women, defective and good, Democrats, Republicans, okay? With a combined total of n objects. Remember, this notation is the notation, alternative notation for combinations. So this was what this would be. This would be, okay? So that should look a little more familiar to you. Okay, so all of these combination probabilities we did in the last chapter, where we had two separate groups and we were choosing without replacement using combinations to count, we're actually using a hypergeometric probability distribution. Okay? Now, again, your I values, your outcome value, can take on all the values from 0 on up to n. Okay? And there are a total of m of one type, right? So say m men and n minus m women. Okay? And I'm trying to pick a committee that has so many men and so many women, right? So balls in an urn that are red or black. Okay? Batch of components that are good or bad. Right, a population of animals that are tagged or untagged, a committee formed of men and women. Okay, so everybody should be comfortable with that. Okay, everybody okay with hypergeometric being not something new, but something you're familiar with? Everybody good with that? Okay, so let me say this is not new up here. It isn't new, just the name is. Okay, so again, I'm just trying to make sure everybody's comfortable with that. All right, let's do some practice, okay? And again, I have a bunch of practice ones that we can work together and some that maybe we can try alone, okay? Again, this isn't a super complicated topic, again, so it should be pretty straightforward. Let's do this one, you try, okay? Take a look at problem 1. Look at the table and answer the questions. Okay, so basically what this is saying is, look at this table and determine whether it describes a discrete probability distribution, why or why not. Okay, so your first answer is yes or no, and then your second answer is a reason. Okay, you can shout them out or type them in the chat. What do you think?
I'm gonna go with yes
Okay.
because it does fit the, or well, what is it? Where'd it go? Not yes. I'm gonna go with no because it's equals to 1, but the -4 isn't between 0 and 1. It's under 0.
Yeah, absolutely. This is not a valid probability. Okay, so what she said was she added up all the numbers and the positive 4/5 at the bottom and the negative 4/5 cancel out. And these two do add up to 1, but it's not a valid probability, right? Not between 0 and 1. Okay, so no. Okay, that's the way you check. All right, if all the probabilities look like they're in the correct range, then you've got to add up the total. If the total doesn't add up to 1 and all the probabilities look okay, it's still not a valid probability distribution. Okay, everybody good? Discrete probability distributions, you can add to get to 1. You can actually do a discrete sum. When we talk about continuous probability distributions, anybody remember from MAT218 how you find the sum of something that's continuous? What's sum in continuous land? Okay, anybody remember? It even has kind of a sum symbol in front of it, but it doesn't look like sigma. Remember definite integrals? Okay, definite integrals are sums of areas under a smooth continuous curve. Okay, so we can do sum, like a sum with counting here because we've got discrete values. But with continuous probability distributions, in order to actually figure out areas manually, you'd need to take a definite integral. We're not going to do that. Don't worry. Okay, we've got built-in functions that do it for us. Okay, but basically, I just wanted to kind of remind you of the connection between sum for discrete things where you're adding up numbers and sum in the continuous world where you're taking a definite integral. Okay. All right, let's take a look at another one. Okay, here's a raffle. A charity is selling a raffle ticket for $1 each. There's a grand prize of $250, 2 prizes of $75 each, and 5 prizes of $10 each. Find the expected winnings. Okay, but first, build a probability distribution. Okay, so probability distribution is going to have an outcome and its probability. Okay, so, well, I could wind up being a grand prize winner, which is $250, but it cost me $1 to play. So the value of the grand prize winning outcome is $249. Okay, everybody remember I have to net out these because it costs me to play the game. Okay, the probability of that is 1 out of 1,000 because there's only one grand prize. The second prize, $75, the net value of that to me would be 74 because it cost me $1 to play the game. And there's 2 of them out of 1,000. Okay. There are third prizes of $10, but again, the net value to me is 9 because I had to pay $1 to play the game. And there's 5 of these. There's one more outcome. What's the remaining outcome? Anybody? What's the remaining outcome? Yeah, I'm out $1. Yeah? How many tickets in the pool are not winners of any kind? How would you figure that out?
Add up the other ones and subtract them from 1,000.
Yep. So if I add 1 plus 2, that's 3 plus 5, there's 8 winning tickets of some kind. Good, Daniel. There's 992 losing tickets. Okay, so there's my probability distribution. Okay, all of these probabilities are between 0 and 1. And if you add them up, you're going to get 1,000 over 1,000, which is 1. So I know I have a valid probability distribution. Now again, for expected value, okay, the expected value of my random variable is each outcome times its probability. And again, you can type this into your calculator exactly that way. Okay? When I did it, I got this. Okay, anybody want to explain the meaning of that expected value? Okay, what does it mean in the context of the problem? Somebody want to explain that to me? Can any one person playing the game lose 55 cents?
No, but on average, a person spending $1 is going to lose 55 cents per ticket.
Right. More importantly, if you average out all the people who play the game, on average, each one of them lost 55 cents, roughly, if you average. Now, either they lost $1 or they won one of the prizes. Yeah, but if you average it out, the average loss is 55 cents. It makes more sense to look at it from the point of the charity, point of view of the charity. On average, the charity made 55 cents on every ticket they sold. If they sold all 1,000 tickets, they made 550 bucks. Okay, that's pretty much what it means. Okay, you don't necessarily lose that amount every time you play, but if you play often enough, okay, on average, you would lose that amount. Okay, part of what's hard to understand in statistics is the concept of an average over a large number of trials, okay, or a large enough population, large enough sample. Okay, all right, let's look at another one. I have a coin that's not fair, it's loaded. Okay, so this terminology means biased or unfair. Okay, and basically it is loaded in such a way that it's far more likely to land heads up. Okay, so the probability of tossing a head is 3/5 instead of a half. Okay, if the coin's tossed 50 times, find the mean number of heads that occur. I'll write the word mean over here. The standard deviation of the number of heads that occur. So the first thing I have to figure out is what sort of probability distribution should I use here? So what probability distribution will model this situation and why? Okay. Anybody have any ideas? We've only looked at 4 discrete probability distributions. Okay, we're counting outcomes here, so it is discrete. I told you 2 of those distributions you wouldn't use, which leaves you with binomial and hypergeometric. So why didn't you ask yourself, does this situation meet the criteria for a binomial experiment?
Yes, because the trials are independent and there's success and failure.
Right. And hypergeometric, they're definitely not independent because you're taking stuff out of the pool, right? Okay, so binomial it is. And if I'm going to do binomial calculations, I need to know n, p, right? And possibly x. But let's do n and p. Okay, n is the number of trials, that's 50. And if I call a success tossing a head, and it's up to me to identify what I want success to be, then the probability of success is 3/5. What's the probability of failure? Getting a tail. Anybody? Yep, 2/5. And you got that by subtracting p, 3/5, from 1. Okay? And just a hint, you can write your 1 as 5/5, and then it's a lot easier to do the subtraction and get a fraction. All right, so I know the mean of a binomial distribution is n times p, and I want to know the average number of heads I would get out of 10 tosses. 50 times, rather. I'm sorry. So 50 times 3/5. My 5 cancels into the 50, and that gives me 30. Okay, so on average, I'd expect to get 30 heads out of 50 tosses with this biased coin. Normally, I'd expect around 25, right? So obviously, if I'm getting a higher and higher number of heads, I'm going to look at this thing and say, okay. Standard deviation, the formula for that is the square root of n times p times q. So that's 50 times 3/5 times 2/5. Okay, I'm going to bring up my TI-84 and share that with you just to show how to do that on a TI-84. Okay, you should be able to see the calculator. All right, and that would be second x squared. That brings up square root. Then it's 50 times. And again, you can put a fraction in here if you want, or you can put actual parentheses. Remember, fractions need to be parenthesized unless you're using your fraction template. Okay, but I can use the fraction template. Okay. So I get about 3.46 for my standard deviation. Again, it didn't render it as a fraction because the square root made that impossible. Okay, so it gave you a decimal. This number can't be rendered as a fraction. In most cases, if you use the fraction template on a TI and it can give you your answer in fraction form, it will. Okay, that saves you having to math frac everything if you need a fraction. Okay. All righty. So let's take a look at this situation. Suppose a pair of dice is thrown 1,200 times. Okay, how many times would we expect a sum of 7 to occur? Okay, so again, we're throwing dice. Okay, pretty much anytime you do things like throw dice or toss coins, you've got a binomial experiment. Okay, so this is a binomial experiment. But the probabilities you might not remember how to do this. My n is obviously 1,200. Okay, what's my probability of success? You have to kind of remember what this looks like. Okay, I have one die that looks like this. Here are my numbers on one die. Here are my numbers on another die. And you're looking at sums. Okay, so if I get a 1 and a 1, that's a 2. Okay, and then I have just filling it in real quick. Okay, here are the ways you can get sums on a pair of dice. Okay, you should be able to see that there are 36 outcomes. Okay, the red numbers that I wrote. How many of them are 7s? Well, there are more 7s than anything else. They're right here on the diagonal. Okay, and you can see there are 6 of those. Okay, so the probability would be 6 over 36. That means the rest of them, if I define getting a 7 as a success, okay, sum of 7, then not 7 happens all of the remaining 30 times. Okay, everybody all right with that? So how many times would you expect on average to get a 7? Well, I'm tossing it 1,200 times, and the probability of a success is that, and multiply that together. I'd expect 200 of those tosses to give me a 7. Okay, any questions so far? Questions so far? Okay. I have 2 more problems I want to share with you because they're similar to what you'd be asked to do in the homework. I mean, these are designed for making sure everybody understands what we're talking about, but let's talk about these 2. Okay? A multiple choice test consists of 9 questions, and each question has an answer that's A, B, C, D, E. So there's 5 possible answers for each question. Only one of the choices is correct. Okay, so there's no all of these, none of these, that's that nonsense. Okay, suppose a student selects the answers to the test randomly. Okay? First of all, you've got to figure out if I want to do this, okay, I want to create a probability distribution for the number of correct answers on the test. Well, how many correct answers could I get on a test that has 9 questions? How many correct answers could I get on this test? How many correct answers could I get on this test? There's 9 questions. Yeah, anything from 0 to 9, okay? So here's my random variable. And I'm going to have 0, 1, 2, 3, 4. I need a second column. 5, 6, 7, 9. So I can get anywhere from 0 to 9 correct. Now, here's my question. Is this a binomial experiment? Well, I can't spell today. What do you think? Good way to check is, can you figure out what N and P are? Well, think of it this way. You're doing the same experiment 9 times, right? You're guessing the answer to a question randomly, okay? The probability of guessing question 2 correctly, given that you answered question 1 correctly, there's no connection, yes? We're assuming the questions are independent. It's not like you've got question 1, part A, B, C, D, where you have to get the first part right to get the rest right. They're independent questions. Okay, so the answer on 1 doesn't affect the probability of the next. And is there a concept of success and failure? Yeah, absolutely. Okay, the idea of success is I guess the right answer. So this is a binomial experiment. It has 9 trials. And what's the probability of success on any given trial? Well, there are 5 question alternatives, 5 answers, and only 1 is correct. So your probability of success is guessing that 1 out of 5, right? So 1/5, or I prefer to use it as a decimal. Okay? That means if I want to figure out the probability of these successes, I can use binomial PDF, okay, on my TI-84. Let me just show you. Turn it on. I'm not going to do them all, don't worry. I'm going to go to distribution, so that's second pairs, and binomial is down the list. Binomial PDF. Okay, number of trials is 9. My p-value is 0.2. And the x value I'm interested right now is 0. Paste. Okay, that's what it pastes in the window. And it gives me my probability of getting none of them correct, which is actually pretty decent, a 13% chance I get a 0 on this test. Now, if I want to keep doing it and filling in the rest of the table, don't go back into the distribution menu. Just do second entry and backspace over the x value. Here's one success, right? I'm going to round that to 0.3020, right? Because the 8 in this position would make that flip over, okay? And then you can just keep doing that for all of the ones in the table, okay? So it does not take a long time to fill in the table. Let me show it to you with the binomial calculator. Okay, this is the one I've embedded in the course, I believe. Okay, probability of success on a single trial, 0.2. Oops. Number of trials, 9. Number of successes, I think I was up to 3. Okay, and it's giving you the exact probability here. Okay, and then all you have to do is go back and change that x value, and it'll keep giving you all the probabilities. Okay, so everybody understand how to use these calculators? Anybody, any questions on using binomial calculators? Okay, I want to make sure everybody can build these probability distribution tables quickly. Okay, you are not using the formula, with the exponents. You're using either the TI-84 or you're using the binomial calculator online. Okay, so I'm going to fill in the rest of these values. Okay, you can see, pretty much our best chance of guessing correct is either 1 or 2 randomly. Okay, these are the highest probabilities. By the time I get out here, this is pretty much, for all intents and purposes, that number 0, okay, of getting all 9 of them correct. But what you want to ask is it a binomial probability distribution? Okay, so each P of X is between 0 and 1. Okay, so yes. And the sum of all the P of X's, I checked it, it sums up to 1.0001, and this is rounding. Okay, because I rounded all these decimals. Okay, so the sum of my probability distribution sums to a 1. Okay, is everybody comfortable with building this? Okay, with building this? Okay, so now I'm going to use my probability distribution to determine the probability that a student choosing answers randomly gets at least 6 correct. That's 6 or 7 or 8 or 9. Okay, and that means all I have to do is add up those values for 6, for 7, 8, or 9 correct answers. Okay, and when I did that, I got a value of, okay, so I picked that because 6 is the threshold for passing the test with the D, okay? There's less than a 1% chance that will happen, okay? So answering more than 6 or more of them randomly and getting them correct, there's less of a 1% chance, okay? So that's what I'm showing you here. Now again, you can do this with binomial CDF, but remember, you have to do 1 minus 5 correct to get that on your TI-84. With the online calculator, it's really, really easy. See how it's done? I'm going to put a 6 in here and calculate. Okay, I want the cumulative probability that it's greater than or equal, and here it is right here. Okay, so the online calculator is actually easier to use than a TI-84 because it gives you all of the probabilities equal to X, less than or equal to X, greater than X, every flavor you want. Okay, so that's kind of what I would recommend. All right, here's the last one. Okay, an elementary school parent-teacher organization, a PTO, has 185 parents and 12 teachers as members. A committee of 5 people is selected at random from the membership. Okay. Create a probability distribution for the number of parents on the committee. Okay. Well, my committee is going to have at most 5 people on it. Okay. So my values of my random variable for number of parents would be either none or 1 or 2 or 3 or 4 or 5. Right? I can't possibly have more parents than are people on the committee. Now I need to figure out the probabilities. Okay, so what do you think? Is this binomial or hypergeometric? Okay, what do you think? Binomial or hypergeometric? Remember, the key is whether you're doing the same thing or if the probabilities change. You're pulling people out of the pool. Yes, okay. So Chelsea's saying it's hypergeometric because you're picking people once, pulling them out of the pool, and once you do that, you change the probability for the next draw. Okay, so not binomial, hypergeometric. Okay, so again, you would have to use something that looks like this. Here are the parents, and you want to choose X of those. Okay, here are the teachers, and you want to choose, we have a total of 197 people. Okay, so again, this would be 5 minus X. Okay, and then down here, it's 197, choose 5. Okay, that's how I'm going to create the probabilities. I did that already. Okay, again, I put a hypergeometric calculator into the calculators that are in that separate module in our course. You can do it using this formula if you're comfortable doing that already, or use the hypergeometric calculator. Okay, it might take you a minute or two to figure out how to use it, but you're always welcome to ask if you've got questions about the tools. All right, so this one, okay, so I have a really infinitesimal chance of getting no parents on this committee. Okay, look at the overwhelming number of parents in the pool. It's reasonable that I get a really small probability. But then the probabilities start increasing as the number of parents increases. And like you think, I would have the largest probability of getting a committee with 5 parents on it. Okay? Because again, there's an overwhelming number of parents in the organization, many, many more than there are teachers. Okay? So using the probability distribution we created, determine the probability of at least one teacher. But remember, my X is tracking the number of parents. So at least one teacher means 4 or fewer parents. Okay, so I need to add up all the probabilities where X is less than or equal to 4. So that's 0, 1, 2, 3, and 4. Okay, and when I add those up, I get about a 27% chance that by just picking randomly, I'll wind up with one teacher on this committee. Okay, if I really want a teacher on the committee and I just want to pick somebody, okay, those are not terribly good odds. Okay, and again, it's because there are so many parents. Okay, anybody questions on any of this? Okay, the last 2 problems are kind of like what your homework's going to ask, so I wanted to make sure people got to see those. All right, I'm going to stop sharing and come back to the meeting. Okay, and again,